So if you want to start recording. Is it being recorded? Okay, I'll assume it is. So,
yeah, it says it's recording.
It's my pleasure to announce our today's speaker is Shirly Geffen. She is based in Münster and in University of, I'm going to say it wrong, Beersheba.
Yeah, that's right.
Very good. And she will talk about decomposable partial actions today. So take it away, Shirly.
Thank you, Karen, and thank you very much for the invitation to give a talk. So the talk is about joint work with Fernando Abadi and Eusebio Gardella about decomposable partial actions. So I want to start with some motivation. So assume that you start with an automorphism alpha on a C-star algebra A. This gives you an action of Z on A. And if you want to compute the K-theory of the cross product, usually you would consider the Pimsner-Voiculescu exact sequence. It looks like this. And this is indeed a fundamental tool in the computation of K-theory of cross products by Z. For example, if you want to compute the K-theory of the rotation algebras, then rotation algebras are cross products by Z, and you can apply this diagram. Now, the problem is that many interesting C-star algebras, they do not arise as Z cross products. For example, unital AF algebras are not cross product by Z. Let me give the argument here. So assume for a moment that we could write a unital AF algebra as A cross Z. Then in this diagram, in this exact sequence here, you would know that the K1 of A cross Z is 0 because K1 of AF algebras vanish. And then also as a consequence, the image of the map delta here will be 0. But by exactness, you know that the image of delta coincides with the kernel of the identity minus K0 of alpha. And it's immediate to see that the class of the unit element of A lies in this kernel. Now, since the unit element of A is the same as the unit element of the cross product, this class never can be 0 unless your AF algebra is the 0 algebra, and this gives you the contradiction. Okay, there is actually a complete characterization for when a C-star algebra is a cross product by Z. This is called Landstadt theorem. And it says that a C-star algebra A is isomorphic to a Z cross product if and only if it admits a circle action, gamma. In one direction, this will be the dual action on the cross product. And it admits a unitary U such that gamma acts on U by just multiplication from the left. So multiplication with the circle value. This unitary in one direction, again, if your algebra is already a cross product, this unitary will correspond to the element 1 in the group Z that is inside a cross product. So this is the unitary, and this is the action, the dual action on it. The other direction is, of course, more difficult, and you can show that in this case, your C-star algebra is isomorphic to the fixed point algebra by this circle action, and cross product with Z, where the action is given by conjugation with this unitary element U. Okay, and then the next step was by Excel. Excel showed that under mild conditions, any C-star algebra possessing a circle action, so like here you have a circle action, but you don't require anymore the unitary, but some milder condition, then it's a cross product, but not by a Z action, but by a partial automorphism. And by partial automorphism, I mean an isomorphism between two ideals in A. For example, then you can show that every AF algebra is a cross product by a partial automorphism. And moreover, he also gives his version of the Pimsner-Breucolescu sequence for partial automorphisms. It looks similar to the one we had above, but here in the corners, instead of the K-theory of A, you will take the K-theory of the ideal I. So this allows you to compute K-theory for C-star algebras that arise as cross product by partial automorphisms. Usually it's recompute because the examples we know are, for example, AF algebras, Toeplitz algebras. In these cases, we already know the K-theory, so this just allows you to recompute the K-theory. But of course, whenever you can view a C-star algebra as cross product by a partial automorphism, you also understand much better its structure. So these are the advantages. And now I want to recall the formal definition. So this is by Excel and McLennan. For a C-star algebra A and a discrete group G, this also can be defined partial actions for locally compact groups, but then you need some continuity conditions. I don't want to get into that. We will actually focus on finite groups even. So discrete is enough for us. A partial action of G on A is a pair consisting of bunch of ideals AG in A indexed by the group elements and bunch of star isomorphisms alpha G from AG inverse to AG. So isomorphisms between the ideals. Notice here that the domain of alpha G is actually AG inverse. And the conditions that you want is, first of all, that the ideal that belongs to the identity element of the group, namely A1, is the whole C-star algebra A. And the map, the star isomorphism alpha 1 from A1 to A1 is just the identity on A. The second condition is that when you compose alpha G with alpha H, so this is not everywhere defined, because if you take alpha H, then the image lands in AH, and it's not clear that AH belongs to the domain alpha G. But whenever you can do this decomposition and it's well defined, then it will coincide with alpha GH. So this is the definition. One example before I go on, one example is if you take all the ideals here just to be the whole C-star algebra A, then you get the usual definition of an action, which we will call a global action, just to distinguish between them. Okay, so an important property that follows from this definition, that the map is that the maps, alpha G, the star isomorphisms, they actually act by translation on these, by left translations on these ideals, on these domains. In what sense? If you apply alpha G to AH, but where you can apply it where alpha G is defined. So on AG inverse, so when you take alpha G and apply to AH intersecting with its domain, then you land in AGH. Of course, you then have to just intersect with the range of alpha. So in some sense, AH is mapped by alpha G to AGH up to intersecting with the domain and the range of the map alpha G. So, and this is true for all GH in G. So as we said before, if we take all AG to be A, then you get the usual definition of a global action. Another motivation to study partial actions is that the flow of a vector field always gives rise to a partial action of R. What we discussed before were these partial automorphisms. These are isomorphisms between two ideals of A. They always give partial actions of Z. How you would define these partial actions, you would just take the powers of theta, and the domains, the ideals, will be determined by where the powers of theta are defined. Another way to have a partial action is if you take two C-star algebras, A and B, where A is an ideal inside B. And you start with a usual global action beta of G on B. Then if you want to restrict an action to an ideal, it's impossible unless your ideal is invariant under the action. Now, if you allow for partial actions, then you can restrict beta to any ideal A inside B. But the new thing you will get, the new alpha acting on A, will be just a partial action and not a global action. So you will do that by setting the domain AG to be the translation of the ideal A by beta G and intersecting back with A. And alpha G will be the restriction of beta G to this AG inverse. So this will give you a partial action of G on A. And partial actions that arise this way, they will be called globalizable. So they somehow, you just restrict the global action to an ideal, and then beta will be the globalization of alpha. And these are quite interesting examples, because then you have quite strong connections between alpha and its globalization, and you can study your partial action alpha via its globalization wherever this is possible. So it's not always possible to globalize a partial action. There is a necessary and sufficient condition for that, but we won't get into that. Okay, so you also want to have cross products by partial actions. This is defined similarly to the way you define cross products for global actions. You take a C-star completion of the following associative star algebra. So you take just finite formal sums, AG delta G, where AG now are not just elements in A, but are elements from the domain AG. And this set is then equipped with the following operations that make it an associative star algebra. So the star is just defined as you do it in the global case. And the product of AG delta G with BH delta H. So AG belongs to the ideal AG, BH belongs to the ideal AH. And if you want to multiply them, usually you would just write AG alpha G of BH delta GH. Now, if you open here the brackets, this is exactly what's written. But if I just wrote alpha G of BH, I would run into the problem that BH belongs to the ideal AH and alpha G is not defined there. So you do this little trick and you write alpha G inverse of AG, this is allowed. You land into the ideal AG inverse, and since AG inverse is an ideal, you multiply with BH, you stay in AG inverse, and so you can apply to this alpha G. You make BH enter the domain of alpha G by multiplying with this element. You just now have to check that this coefficient indeed belongs to AGH, so that you can put it as a coefficient of delta GH, but this is just simple and I wouldn't do that. Okay, so this way we get the partial cross product. And now I want to give the definition of invariant ideals. So when you have a partial C-star dynamical system, you say that an ideal J in A is alpha invariant. Usually you just say if alpha G of J lands inside J. But here you have to intersect just with the domain of alpha G, as we usually would do. So alpha G of J intersecting with AG inverse then is mapped to back to J. And you require that this happens for every G in G, then you would call J an alpha invariant ideal. And as in the case of global cross products, whenever you have an invariant ideal, you would get a short exact sequence of C-star algebras looking like this, where here on J and on A mod J, you get naturally induced partial actions. Okay, so I want to say what is our motivation. So we define a property of partial actions, especially partial actions of finite groups, which we call the decomposition property. And partial actions with this property will be very, very accessible and easy to understand. And they also occur naturally. So this is the important part. We will show that every partial action of a finite group is actually an iterated extension of the composable partial actions that we can understand very well. And we also will give a complete description of cross products associated to these decomposable partial actions. This will be essentially just direct sums of cross products by global actions. So we will understand partial actions by decomposable. Sorry. Yes, we will start with a partial action, general partial action. We will view it as an iterated extension of partial actions that are very beautiful, and these very beautiful partial actions, we will completely understand their cross products. So that's essentially the motivation. So I want to start with the example that at least motivated us. So we start with the group Z mod 4Z, and denote its elements by just 0, 1, 2, 3. And it acts partially on some commutative C-star algebra C0 of X. So whenever you have a partial action on a commutative C-star algebra, using Geffen duality, and as you do for global actions, you can just think of it as a partial action on a topological space X. But what do I mean by partial action on topological space? Instead of ideals, you will take open sets. And instead of star isomorphisms between the ideals, you will take homeomorphisms between the open sets. And this is then will be with bijective correspondence with partial actions on commutative C-star algebras. So yeah, Geffen duality gives a bijective correspondence between partial actions on commutative C-star algebras and partial actions on locally compact Hausdorff topological spaces. So what I mean here by G acting on C0 of X, I mean that I have the following picture. I have X0, which is the whole space, the open space that is associated to the identity element of the group is the whole space. And then inside, I have open subsets of X0. For every element of the group, 1, 2, and 3, I associate some open subset. And these are my domains. So this is the picture. I don't know how they intersect with each other, but that's the general case. And then I claim that I have the following short exact sequences. So first of all, I can restrict my partial action to the intersection of all the domains. So when I intersect finitely many open sets, I get an open set. And since my partial action is just acting by translation, as we discussed in the beginning, when you start to translate something that is in the intersection of everything, you just stay in this something all the time. So on this little black part, the restriction of your partial action is actually a global action. So the first thing you get is the following short exact sequence, where here on the left-hand side, you just have a global action. Now we want to go on and see what we are left with. So we are left with X minus this black part. And now we take the red part. I claim that also the red part now in the new system, after we remove the black part, the red part will be an invariant subset. And this will be also, the restriction to the red part will be also something that we understand very well. So that's the advantage. In the left-hand side, we have then the red system that will have what we call the decomposition property. And so we can understand its cross product. And then we go on. And of course, the next set that you will take in this invariant is the gray part. Also here, we will be able to restrict our partial action to this gray part and completely describe the cross product. And finally, after we remove everything, the black, the red, and the gray part, we stay with something that is, with some partial actions that is restricted to this white area. And so in this white area, as you see, there are no non-trivial domains. So because you essentially removed everything. And you remember in the cross product, you took to the coefficient delta G, you took elements that belong to the domain AG. But now after removing everything, except of the trivial domain, the cross product just becomes the base algebra. So the cross product will be only this white part, and all the other delta G will have just empty or zero coefficients. Yes, so these algebras that we get as a quotient, all its domains are zero except of the trivial domain. And so it will be simply just a commutative C-star algebra, C0 of X minus all these colored parts. So the idea is to understand the original partial action that we were given on C0 of X by just making these iterated extensions. At each level here, in each sequence here, we will understand the left-hand side of the sequence. We will be able to completely describe it. And we also will be able to completely describe the last quotient. So all these systems on the left and the last system will have what we call a decomposition property. And I have to now say some more formal definitions. So when you start with the finite group G and the C-star algebra A, then for n in N, for a natural number, we set tau n to be just all the subsets inside G that are of cardinality n and contain the identity of the group. And for a partial action alpha then, and the tuple tau in tau and G, so just a subset of G of cardinality n that contains the identity, we will start to intersect, we will define A tau to be the intersection of all elements G that belong to the subset tau, AG. So this is just intersection of some ideals. This is still an ideal. And this is this is an ideal in A. So I want to give you maybe an example using this picture. So assume that you gave me a subset of G, which consists of 3 elements, 0, 1, and 2. So it always has to have the 0 element of the group. So you give me 0, 1, and 2. I look on the intersection of x0, x1, and x2, and then I look on this part. So this is my A tau, where tau is 0, 1, 2. And then 0, 2, 3 will be intersecting x0, x2, and x3 and getting this other part. So I will say that my system has a decomposition property, for example, this red system, if it's a sum of these A taus. So it's the sum of these areas that belong to the tuples 0, 1, 2, 0, 2, 3, and 0, 1, 3. And on top of that, if you take one of these A taus, for example, 0, 1, 2, and you intersect it with an element that does not belong to 0, 1, 2, for example, 3, then the intersection is empty. And why this is true? Because if you start to intersect 0, 1, 2 with 3, you exactly land into this black domain that we already removed. So we say that alpha has the n decomposition property if A is this sum of the A taus. And when you take A tau and intersect with AG, and G does not belong to tau, then this intersection is trivial. Okay, so I want to give some examples. Assume that alpha is a partial action of G, a group of order n. Then I claim that it has the one decomposition property, if and only if all the domains except of the domain that belongs to the identity element are 0. And why this is the case? One decomposition property tells me, okay, look on tau 1 of G. Look on subsets of G of cardinality 1 that contain 1. So this is only the singleton 1. And then your sister algebra has to be A1. This is trivial. This doesn't mean anything. We know already that A1 is A. And the second condition tells me that A1 intersecting with AG, whenever G is not 1, is 0. So every AG is then just 0. And on the other extreme, it has the n decomposition property where n is the cardinality of the group G, if and only if it's global. And why this is true? Because again, you take a subset of G of the cardinality of the group. Only one subset is possible to take here is the whole group. Then this second condition tells you nothing because every element belongs to the group. So second condition just doesn't give any information. But the first condition tells you that your A is the intersection of all the ideals. Because A tau is just the intersection of all G belongs to tau, and tau is the whole group. So A is the intersection of all the ideals. This exactly means that your action is global. So you see, when we have the one decomposition property is the last system that we had before, the system where we removed all the ideals. And the n decomposition property is the black system that we had in the beginning. And then comes this theorem that we saw essentially by example. Any partial action of a finite group is an iterated extension of decomposable ones. More precisely, if G is finite, then there are canonical equivariant extensions looking this way, where you start A1 alpha 1, you start with your original system A alpha. At each level, you require that these ideals, dk delta k, they have the k decomposition property. And the very last system that we will get as a quotient has the one decomposition property. So this means that to understand alpha as good as we understand global actions, it suffices to understand all these delta k's, all these systems that have the decomposition property and the extension problem. Okay, the next theorem is saying that indeed we can understand these decomposable partial actions. Let AG alpha be a partial action with the decomposition property. Then the cross product will be some direct sum over matrix algebras over some global cross products where JJ will be just some ideal A. We can describe them explicitly, but I don't really want to give this explicit description here. JJ will be ideals in A, and HJ will be some subgroups of G that act globally on the JJs. And the cross product is just essentially direct sum over matrix algebras over regular cross products. And I don't want to give the complete description, but I do want to discuss an example how we do that. Okay, so I start here. So we know that the red system, for example, has a decomposition property, and I want now to tell you how we can describe the cross product. So now just look on the red system. We forget about the rest. We fix some tuple, for example, 0, 1, 2. And we know that we can apply on 0, 1, 2 the maps alpha 0, the inverse of 1 in Z mod 4, which is alpha 3, and the inverse of 2 in alpha 4, which is alpha 2. So when we apply alpha 0, we just same place. When we apply alpha 3, remember that our action is just acting essentially by translation. So if you translate this set by 3 modulo 4, so you add 3 modulo 4, you will get 0, 3, 3 plus 2 is, so 0, 0, 1, 3. If you add 3 modulo 4 here, and so you know that your action alpha 3 will move you to this tuple. Now, if you apply alpha 2, you again just need to translate, in order to understand what the action does, you just need to translate this set 0, 1, 2 by 2 modulo 4, and then you will move to 0, 2, 3. So you will move here. So you apply alpha 0, you stay in place. You apply alpha 3, you move here. You apply alpha 2, you move here. And we can show, therefore, that the cross product by this on this red system is just 3 by 3 matrices over this one of the red parts. That would be essentially the idea. And so this is then gives you a complete description. But I did not tell you how you ever get global actions. So here is another example where you see a little different picture. Now just look on the gray part. I want to explain what, or to understand what is the cross product. So first, as we did before, we fixed one tuple and we see how it moves under the action. So we fixed, for example, 0, 2. We can apply 2 maps, alpha 0 and alpha 2. When we apply alpha 0, we stay here. When we apply alpha 2, it's again just translating by this set by 2 modulo 4. So you add 2 modulo 4 here, you just stay in 0, 2. Then this gives you essentially a global action of the subset or the subgroup 0, 2 inside Z mod 4, which is just Z mod 2. It gives you a global action of Z mod 2 on this part. Because you just apply alpha 0, alpha 2, you stay in place. And then it gives you a direct sum with what happens with the action when it's restricted to this place. So you can apply, for example, alpha 3 and alpha 0. Alpha 3 will move you here. Alpha 0 will stay, keep you in place. And so you will get 2 by 2 matrices over this domain. So this is essentially how we understand the cross product. And as a corollary, we know that we deduce that if P is a C-star algebraic property that passes to global cross products that by finite groups, ideals, direct sums, extensions, and matrix amplifications like we have here, then if A has property P, then also the cross product by the partial action has property P. Because we know that the partial action is just iterated extension of the composable partial actions. And for the composable partial actions, the cross product is just a direct sum of matrix amplifications over global cross products on ideals. So these are essentially the properties that we need to preserve. And for example, P can be nuclearity. Okay, so another thing that I want to discuss and I find quite interesting is the partial group C-star algebra. This is the analog of the group C-star algebra in the non-partial case. So this is the universal C-star algebra with respect to partial representations of G and not just representations of G. By partial representations of G, I mean maps U from G to P of H that satisfy the following properties. So when you take UG-UH, it's not UGH, but it's UGH up to multiplying with the witness UH inverse. And U1 is 1, and UG star is UG inverse. Now you can check by taking here H to be G inverse in this equality. You can check that this this implies that UG star UG is UG. So these UGs are not unitaries, but they are partial isometries. And clearly, since every unitary representation is in particular a partial representation, you have a surjection from the partial group C-star algebra to the full group C-star algebra. But the partial group sister algebra catches more information about the group. For example, if G is abelian, the partial group sister algebra may be non-commutative sister algebra, in contrast to the group sister algebra. For example, one can show that the partial group sister algebra of Z4, Z mod 4Z looks like this, while the partial group sister algebra of Z2, Z mod 2 cross Z mod 2 looks like that. So it looks completely different. While when you take just group sister algebras and abelian groups, then the group sister algebra is completely determined by the cardinality of the group. And here you have two abelian groups with the same cardinality and completely different partial group sister algebras. So it catches more information about your group. And what we can show is we can show that these partial group sister algebras are isomorphic to a direct sum of cross products by decomposable partial actions. And since we completely can understand or describe cross products by decomposable partial actions, we can describe explicitly partial group sister algebras of finite groups. So we do this by hand, and we were quite excited to get, for example, these two computations here. And this, however, was already carried out by Dukhochaev, Excel, and Pizzione using different ideas. And another thing that I want a little to mention is nuclear dimension. So I give a little motivation for what a nuclear dimension is. So a nuclear dimension is a non-commutative analog developed by Wilhelm Winter and Joachim Zacharias of covering dimension, of Lebesgue covering dimension of topological spaces. In the sense that, I mean, if you take the nuclear dimension of C0 of X, then it coincides with the covering dimension of X whenever X is a metrizable, locally compact Hausdorff space. And a nuclear dimension has the following permanence properties. If you have a short exact sequence of sister algebras, then the nuclear dimension of the ideal and the nuclear dimension of the quotient are both bounded by the nuclear dimension of A. The nuclear dimension of A, however, is bounded by the sum of the nuclear dimension of J and the nuclear dimension of the quotient, n+1. If you take matrix amplifications, then the nuclear dimension is preserved. A nuclear dimension of direct sums is bounded by the maximum of the nuclear dimensions. So these are the nice properties. And with these properties, I want to show you that if you have a partial dynamical system with G a finite group acting partially on C0 of X, and X is a locally compact Hausdorff second countable space, then the nuclear dimension of the partial cross product is just bounded by the dimension of X. Now this result, we will prove it using these iterated extensions, the permanent properties of the nuclear dimension, and the fact that this is already known when G acting globally on C0 of X. So I remind, we have this kind of iterated extensions, and we want to bound the nuclear dimension of this sister algebra, this cross product. So we start to decompose it this way. And we know that here in the left systems, in the ideals, we all the time just have, we have decomposable partial actions. So we have a complete description of this cross product by just matrix amplifications, direct sums, and global cross products of subgroups of G on some ideals inside the algebra. So in each of these left-hand sided systems, we know that the nuclear dimension of the cross product is bounded by the dimension of X. Okay. Using these known results for global systems and using the permanent properties of nuclear dimension. So all of them we can bound by the dimension of X. And also this last system, we said this is just a commutative sister algebra. And so also here the dimension is just the dimension of this space, which is still less than the dimension of X, because this is a subset of X. Okay, so in order to bound the nuclear dimension of this guy, we have essentially to sum the nuclear dimension of this plus that, plus this, plus that, plus this, plus that, plus 1. But the problem is that you will get something that depends, some bound that depends on the cardinality of G, because you each time sum the dimension of X, yeah, because you have this, you have the nuclear dimension of A for extension bounded by the sum and not just by maximum or something like that. But the way you somehow avoid summing is you notice that all the systems or all the cross products that are involved here, they all subhomogeneous sister algebras. And for subhomogeneous sister algebras, the nuclear dimension of the extension is not bounded by the sum of the nuclear dimensions, but by the maximum. And so this way you just get the dimension of X and you forget about the cardinality of G. So main idea of the proof, as I described, uses the iterated extensions, the description of cross products by partial actions with the decomposition property, the results for global actions, the non-results for global actions, permanent properties of nuclear dimension, and finally show that the iterated extensions consist of subhomogeneous sister algebras, and that's essentially the main idea. Some general remark. In general, it's not known, even in the global case, whether nuclear dimension of A finite implies that nuclear dimension of the cross product is finite for finite group G. And this is one of the main motivations for the concept of Rokhlin dimension. With the concept of Rokhlin dimension, one can show that at least for finite groups, if the nuclear dimension of A is finite and the Rokhlin dimension of alpha, which is some invariant of the action, is finite, then the nuclear dimension of the cross product is also finite. And so we want to have something similar for our partial actions. And so we develop this concept of Rokhlin dimension for finite group partial actions. Let's assume for simplicity that A is unital, although everything can be done also in the non-unital case. So I want to give the definition. So we say that the Rokhlin dimension of alpha is at most D, where D is some integer. If you can find positive contractions, FGJ, that satisfy the following properties, I want to first run this and then explain. So maybe I start by explaining what is just the Rokhlin dimension, not for the partial case. You will have D+1 towers of positive contractions. And in each tower, you will have positive contractions that are indexed by the element of the group. And these positive contractions in each tower, they will have to be almost orthogonal. This is here condition 2. They will have to be almost central in your sister algebra with respect to finite subset. This is condition 4. And in each tower, you will have that the action acts on these elements by translation. So alpha G of FH is mapped to FGH within each tower. You can forget in the meantime about this X here. And all the towers together, if you sum them up together, they almost sum up to the identity element of the sister algebra. And that's how one defines Rokhlin dimension for global actions. For partial actions, we on top assume that FGJ, the element in tower J that corresponds to the element G in G, is in the ideal AG. And then, of course, when we want to apply alpha G to FH, it's impossible unless we multiply with something that belongs to the domain of alpha G. And then we know that alpha G indeed maps FH to FGH and somehow keeps X just alpha G of X, maps X to alpha G of X, of course. So with this definition, one can show that for the trivial partial action, namely the partial action that has all its domains 0 except of the trivial one, the Rokhlin dimension is 0 because you can take all the FGs to be 0. They have to be 0 because they belong to AG, and AG is 0 for all G except of 1. And the element that belongs to the ideal A1 is just the 1. The unit of the C-star algebra, then you will show that alpha is Rokhlin dimension 0. And that's quite interesting because it's it's very different from the global case. In the global case, when you have a trivial action, it will never have the finite Rokhlin dimension, because when you have a trivial action or the identity, it never translates the element. So here you are allowed to take the positive contractions FGJ, not from the whole C-star algebra, but from AG, and that's why you can take them to be 0 and gives you Rokhlin dimension then 0. So we can show that if G then acts partially on X and the dimension of X is finite, then freeness is equivalent to finite Rokhlin dimension. This is also known in the global case. In this case, you even can completely bound the Rokhlin dimension of alpha in terms of the cardinality of the group G and the dimension of X. And of course, you would like to get more examples by starting with some global action, knowing that this global action is a finite Rokhlin dimension, restricting to an ideal and say that the partial action you got also has finite Rokhlin dimension, but this is unfortunately not true in general. Also, it's not true that if you start with a partial action that is globalizable, then the globalization and your original partial action will have the same Rokhlin dimension. But we can show that if the algebra is unital, the C-star algebra is unital, then indeed the Rokhlin dimension of alpha and its globalization, when exists, coincide. Okay. Of course, the main interest for us to study Rokhlin dimension was to study this in order to study the structure of cross products, as it also was done in the case of global actions. And indeed, we get that finite nuclear dimension passes to cross products by partial actions with finite Rokhlin dimension. Actually, you can bound the nuclear dimension of the partial cross product by something that looks like this. Now you will just use essentially the iterated extensions and the fact that you know at each level that you deal with something that is very much related to global actions. And for global actions, you know the result. That's why you get this cardinality of G here involved in the bound, because you have to sum up in the iterated extensions the nuclear dimension at each level. And in general, you don't have subhomogeneous C-star algebra, so you cannot get rid of this cardinality of G. This is a little disappointing here because this means that if we want to extend our results to infinite groups, then we have to come up with a different idea so that here we don't have the cardinality of the group involved in the bound. Also similar to the case of the global actions, if A is an AF algebra and the Rokhlin dimension of alpha is 0, then the cross product is again an AF algebra. Again, you use the iterated extensions, the known results in the global setting, and the fact that being AF algebra passes to extensions. Also, finite stable rank passes to cross products by partial actions with finite Rokhlin dimension. And again, and you also will ask here now that all the towers, all the FGJ, they almost commute. This is a requirement, but it essentially also follows from the iterated extensions and the results for the global setting. And finally, we also generalize this. So if you have finite Rokhlin dimension with commuting towers, then absorbing a self-absorbing C-star algebra passes to cross products by partial actions. Again, using the fact that absorption of a strongly self-absorbing C-star algebra passes to extensions, to ideals, to direct sums, and so on. Okay, and that was everything I wanted to say.
So thanks very much. That was a very nice talk. You have some very nice.
Thank you.
Now we got some clapping. Does anyone have any questions so far? Okay, if not, maybe I can ask a question. You had this result by Rui, I guess it was, that certain circle actions, if you have a circle action, then you automatically get, you know that it comes from a partial action.
Yes.
Is there something similar for like more general groups than Z?
Yes, so yeah, that's interesting actually. I mean, this Landstadt theorem that tells you exactly when a C-star algebra is a cross product by Z, I think I mentioned it quite in the beginning, this result is completely general. So if you take any locally compact group G, one can completely characterize cross product C-star algebra that are cross product by G. And this indeed also was generalized to the partial setting in full generality by Quigg, I think. He had this complete generalization of Landstadt result to partial cross product, or to partial C-star actions on C-star algebras.
I guess the cross product in general will look like some sort of C-star algebra of a Fell bundle over the group, or the dual of the group.
Yes.
And if you in general have something like that, is that when you can say you have a partial cross product or sorry, partial action, or do you need a little bit more?
You need a little bit more, because essentially if you take the C-star algebra, if you take any C-star algebra, you can define a partial action by just setting all the ideals to be 0 except of the trivial one. Then the cross product again will just be the base algebra. And so one has to really require a little more. And yes, so one has to really little deal with spectral subspaces and dual actions, and then to have these requirements on top in order to get the cross product this way. Yeah.
Okay. So it's something like you need like semi-saturated.
Yes, semi-saturation is the right thing. Yeah.
And so in this case, for example, for Z, I mean, there's this notion of these cross products by bimodules that's also XL, but with Abadi and somebody. Eilers, maybe?
Yes.
Yeah, thanks. And they also have this characterization that if you have a circle action and semi-saturated subspaces, then you know it's a cross product by a bimodule. So I guess these are actually basically the same thing, cross product by bimodule cross and a partial action by a partial action in that case.
It might be. I'm not aware of these results with the bimodules actually.
Yeah, I can send you because I mean, something similar to what Marzia and Maria Stella and I are working on actually. But in our case, instead of looking at a partial action, we have actual automorphism of X, but then we have it sort of twisted by a non-trivial vector bundle. And this also gives you a circle action on the resulting algebra. And I'm just trying to think of what the partial action would be on in this case. So if you have a partial action, do you always have, so if you have a partial action on C of X, C of X itself, it's always in there in the cross product.
Yes.
And is it going to be a Cartan subalgebra?
I think if the action is minimal, yes.
Sorry, minimal or something less stronger. Because in the automorphisms, okay, just topologically free is enough.
Ah, yeah.
And also I know that the concept of topologically freeness is available in the context of the partial actions.
Yes, yes, it's available and it gives you that topological freeness, for example, with minimality gives you simplicity. And I think that also that C of X will be then a Cartan subalgebra inside the cross product.
Because also I was looking for this, but I could not find any paper or any work.
Maybe minimality. Okay, no, never mind. Never mind. Ignore what I was about to say.
Because in the case of the homomorphisms, not partial one, topologically freeness is equivalent that C of X is a maximal abelian in the cross product. And I was wondering that if we have this kind of the characterizations for partial actions, even partial automorphism.
Yes, I remember that at some point I used that minimality, but I think I used minimality plus freeness. I mean, this is a little different in partial actions. With that, I think that minimality does not imply freeness, and in the
I think that's true even when you're not
case
Z actions probably.
Yes, in the global case it's implied, and so I think sometimes you have to really require both minimality and topological freeness with partial actions of Z. But Cartan subalgebra, I think I had used it at some point in. I have one paper that is only I am the single author there. So in this paper, you probably can find this, that I use the C of X inside C of X cross Z. This is Cartan subalgebra in some cases, but and then you probably can see what I used there. I don't remember.
So I will look at your paper. Thank you.
Do we have any other
By hand similar to
questions? I had a question and now I think I forgot it. Okay, so you can do these globalizations of partial actions. If you have a partial action that you get by restricting a globalization to ideals, and then you globalize it, I think sometimes you have to change the C-star algebra, right?
Yes, usually we would say globalizable if the space where the globalization acts is minimal in some sense. So you want that the space will be generated by the translations of the ideal. Okay. Because whenever you have a globalization, you can always restrict it to the translations of the ideal, and you will have an action a global action that is acting on this sub C-star algebra. And this then will be called the globalization, because in some sense it's minimal, and this also then gives you some uniqueness of globalizations. So that if a partial action is globalizable, then this globalization is unique up to strong equivalence.
Because what I'm sort of thinking of is that there's this notion of these orbit breaking subalgebras when you have a Z action on C of X. Where you can break the orbit at a small set in C of X, and then you get a sub C-star algebra with a cross product, and you can view this as a cross product of a partial homeomorphism. And because this set is small, somehow these two C-star algebras share a lot of properties. So for example, they'll have the same tracial states, and you can compare K-theory and junk like this. I'm just kind of wondering if somehow you could go in the other direction. If you knew you had a partial action, could you characterize somehow its globalization in such a way that you would have this sort of C-star algebra that's large inside the globalization? That kind of makes sense. So you would need something like, I guess this partial action would be minimal. Is there something where you know you have a minimal partial action and the globalization will still be minimal? I guess that would be the first thing to look at somehow.
Yes, I think this can be shown that globalization is still minimal. I think so.
So it means that the simplicity goes, they share simplicity.
They would share simplicity then, I guess, yeah.
Yes, they are Morita equivalent actually, and so they share the idea.
Many
lattice.
The globalization, sorry, they're Morita equivalent, the globalization and the partial.
The cross products, yeah, the cross product by the globalization and the partial action, they are Morita equivalent. So they will share, for example, simplicity.
Okay, so then in this case, this is not quite the same thing. In the case of an orbit breaking algebra, you can get different K-theory, for example, so they can't be Morita equivalent.
Okay. See.
This is somehow, yeah, slightly different globalization.
Interesting.
I guess it could have more than one. On the other hand, if it's just, no, it still won't have the same K1 actually. All right, anyway, I'm just sort of wandering off in my own thoughts now. So I'll just check once again if we have any other questions in our audience. Feel free to speak up. And if not, maybe we can just thank Shirley again for a very nice talk.
Thank you very much.
And next week, we have, I think, our final talk of the year, which is going to be by Marco Matassa. And we'll be returning to the realm of more non-commutative geometry type stuff. Let me just put up his, if I can find it. Give me a second, and I'll share my screen. All right, so, oops, hold on.
I should stop sharing maybe. And then...
No, there we go. All right, I have two screens because I'm also putting this on a projector and I'm having difficulty moving between the two apparently. Okay, so here we go. This is a talk. So I hope some of us will be there, and so yeah, thanks again.